Okay, so welcome everybody. My name is Colin Caprani. I'm an associate professor at Monash University in Melbourne. And Justin?
Hi everyone, my name is Jun, or you can call me Justin. I am a research officer here. I work under Colin. I'm based in Monash, Malaysia.
Great.
Yeah.
Good. So yeah, will you share your screen, Justin? We can get started. We'll just have a quick kind of introduction. Then Justin will get into a kind of reasonably detailed example of the package, and we'll go through documentation, and then at the end, kind of a call to action, just kind of what the next steps are. So. Great. So thanks for joining us, everybody. So we've done the introductions. So yeah, the kind of talk has been promoted by our university, of course, and the Institute of Structural Engineers here in Australia, which is great. So we've kind of nearly done the introduction, I guess. This is the overview I've mentioned. We'll get to the Q&A as well at the end and get your thoughts. So we've got an example of one of our grillages here on the right-hand side. And consistently, you'll see that the XZ plane is the horizontal plane that we're working with, and the Y-axis is the vertical axis. So just to orient you on our grillages. Great. So why why OpenSees Pi for grillage modeling? Well, OpenSees is a fantastically capable open source finite element analysis package used extensively in earthquake engineering in particular. But what's amazing for structural engineering is its absolute flexibility in the modeling of members, cross sections, and its nonlinear analysis capabilities, coupled with dynamic and static. So OpenSees is incredibly powerful, and when it's coupled with a wrapper or an interpreter called OpenSees Pi for Python, it brings the power of OpenSees into the Python ecosystem. And of course, once you're in Python, you can really do anything with it that you want to do. And if you're familiar with Python, toolboxes like Pandas and NumPy make it so powerful that you're able to really do a tremendously innovative engineering workflow in that ecosystem. So one of the gaps we saw, which for our own research purposes, was that we want to do grillage modeling extensively and parametrically, so that we want to produce perhaps 100 grillages and run live load models over 100 grillages. Now, to do that in commercial software would be, well, basically impossible. And so getting into this space of scripting a grillage modeling capability is what the need was for us. On the left here is kind of some typical, commercial software, what you'll see in there, different types of models, and beautiful extruded bridge decks and things. There will be no beautiful extruded bridge decks. What there will be is very, very powerful scripting interface to grillage modeling. To do a traditional grillage in OpenSees would have been quite challenging, even with OpenSees Pi, because you can see the screenshots here in front of you. Every single load at every node point on the grillage would need to be identified properly. And of course, with grillages, we want to move the loads. We want to have traveling live loads. And this means that every position requires a completely new load distribution across the bridge deck. So this gap is what OSP grillage fits. OSP for OpenSees Pi and grillage, because grillage models. And most of our coding effort, if you've had a browse through source code, is in terms of distributing loads to nodes, managing load cases and load combinations, and so on. OpenSees is the analytics engine at the back end. So it's kind of a wrapper for OpenSees Pi, which is a wrapper for OpenSees. So we have aimed to make the interface simple as possible. Obviously, it's bridge engineering. It's not tiddlywinks, but as simple as possible. We think that the interface functions are kind of well named and reasonably named, and they do what they say on the tin. So we've aimed for that simple API. We'll see in the example, we think it's a reasonably quick generation of a grillage model, and we'll see again why that's the case once we've got all those load cases on combinations set up. One final point for researchers in particular is the ability that, having generated the grillage model, we can export the PI file, which contains the sequence of OpenSees PI commands. Why that's useful for researchers in particular is because they can then manually edit that file to do more advanced analyses, to change the element types, to introduce fiber sections, whatever a researcher might be interested in a bridge deck, that otherwise they would have had to hand craft the grillage model in there. Because this wrapper produces the PI file, it gives a kind of great flexibility in that regards. For maybe more practitioner or the research that we might do, where we're interested in looking at bending moments and beams and so on from a static analysis, ospgrillage can produce that analysis, as we'll see. So I'll hand over to Justin for really the meat of today's workshop. So thanks, Justin.
Thank you, Colin. F12, there we go. All good with the screen. Yep. Okay, so what we have here is really us applying OSP Grillage on a real life example, or rather a Grillage model that we have here that Colin studied, and Colin and our team studied previously. And so this is to showcase that we can actually showcase the features of OSP Grillage, showcasing the little steps, especially the steps on how to create and up to the point at the end to get the results. So this is introducing our bridge first. So this is our bridge cross section. It's a 33.5 meter long bridge deck. It's a Super T bridge with 5 beams. They're all Super Ts are common structure forms found in Australia. And what we want to do here is we want to model, as per standard grillage analysis, we want to model the beams as a node line, and then we'll model the parapets at the side as well as node lines as well. So top you see the section, bottom you see the intended dimensions of the bridge deck in the Z direction, which is the transverse direction. So transverse is 11.565 meters wide, and span is 33.5 meters long. Now we using Python, the way some of you may be familiar how Python works is that we do imports. So after installing the OSP Grillage, later on we'll answer questions about installations. But having installed OSP Grillage using pip, we just simply import it using Python import module, import OSP Grillage as OG. The other 2 lines here are just little tweaks for our presentation to make it so that the plots fit in the slide you see, because ours is too big, and obviously Matplotlib is just the showing the back end of showing the plot features up later on in our slides. A little good thing that we like to do here in our team is we usually define our units in our OSP in our Python scripts. So later on you see all these units popped up beside the numbers, which helps you keep in track of what's the units of the readings or numbers here, which is quite helpful, quite useful to tracking down the magnitude and keeping things consistent. So the first step ever of, I would say, the whole OSP Grillage process is, I would say, is the creating the materials. Now, create material. Earlier, we emphasized that we try to provide as simple interface as possible, and here it is. OSP grillage, you just simply create a material using this create material functions, and there will be more functions like this later on as we speak. So for our model here, we create a concrete model, and since it's an Australian bridge, we try to match its properties with the codified material properties in AS 15100. For this example here, we followed what we studied previously. We adopted the grade 65 MPa concrete here. So we have, so as an alternative, if you don't want to use all these codified materials, we also allow you to create custom material, define custom material properties. So the main three properties that you need to define is E, elastic modulus, Poisson ratio, V, and density here. So what OSP grillage will do is to take in these properties and it wraps around OSP OpenSees material and creates the appropriate material for your custom material properties here. So that's the simple step of creating a material. Same thing, cross sections. So as you saw earlier, there are various cross sections to be defined on each node line to represent each section of the grillage, the longitudinal beam. So you have B1 to beam 5. So beam 1 and beam 5, they are called exterior main beams. They are a bit different to interior main beams, which is beam 2, 3, and 4, because they have a slightly narrower flange width. And so in our example here, we will define the two beams separately as different sections. And also we'll define the edge beam as to represent the parapets, right, left and right. And last but not least, when we're looking at transverse direction, we also need to define properties for the transverse slab. In OSP grillage, how we do that is using again a simple interface of create section function. So create section function is as shown here. We create the four objects here. So at a minimum, create section requires you to specify the area of the section, requires you to specify the elastic modulus Iz and Iy. Note that Colin mentioned earlier that we are working in the space of x being the longitudinal direction and z being the transverse directions. And so Iy, Iz corresponds to the bending moment about Iy, and Iz about z-axis respectively. So following through, we just define all four sections. After having created material object and the four sections of our grillage model, we now go to create the grillage member itself. So grillage member requires two things, which is a material and a section for it. So here we have again a simple interface to create the grillage members. Now this grillage member are required to later on be set to the grillage model. So very simple step here is just create member function, and it goes set section as the previously defined section, and concrete material as the material for the grillage member here. And here we just do for all four, for the longitudinal beam being the interior beams, edge longitudinal beam being the those of the side of the grillages, the edges, and last but not least, the transverse slabs as well. You got the intermediate transverse slabs in the middle, and then the edges of the transverse slab. We create a section for that. So having defined our grillage members right now, we then go to create the actual model, the actual dimension, the actual mesh of our model. So how we do that is, first, we recall that the bridge is 33.5 meters long, and 11.565 meters wide. In Python, as we first define its variables here. Also note that we in our model here, what we don't do is we want to have, as we've seen earlier, we want to have 7 nodes along the z direction, and so we have n underscore l as 7, and then for our bridge we want to have 10 equally spaced node spacing along the 33.5 meter longitudinal span, and therefore we chose 7 and 11 nodes here. So NL and NT are the number of nodes you want, number of members nodes you want to define in Z and X direction respectively. And we have here at the end edge distance. Edge distance is that distance between the first exterior beam, as you saw earlier, is 1.05, and then the last variable I would say is more or less the distance between the exterior beam, that beam 1, and beam 2, the first interior beam, which is 2.2775 here. ospgrillage has a feature which we will not show in this example here, but we have shown in our documentation that we can produce a skew mesh. We can introduce skew angles to our mesh edge, and then it will tilt accordingly. It will generate the node points accordingly as well. But however, for this example here, since it's just an orthogonal bridge, it will just be angle equals to 0. If later on when we go to the documentation, we can look at some examples there that already have some different angles you can explore. Creating the grillage, again, simple interface, a simple function called create grillage. Now all the properties here are just the inputs required. So I would say more or less these are what we defined earlier. Putting in the only new variable being bridge name. That's the only new variable here. Now after we create the model being right here, the object, the grillage object in Python, we then now start setting members, assigning members to our grillage model here. So how we do that is, again, a simple set member function. So the unique thing about what we do here in ospgrillage is that we have a set of standard grillage element names that we have. So what you see here under the line 14 here, interior main beam, exterior main beam 1, exterior main beam 2, H beam, etc. So these are the standard grillage elements which you pass through the grillage member object defined previously into set member, and to say set longitudinal beam as member interior main beam, it will automatically set that defined grillage member properties to those elements along that dot line of the interior main beam. And this is the same for transverse direction as well. Yep, I think I'm missing one. Oh yeah, last step. So really this is the last step to create the model stage. So creating model is create OSB model function. So what the py file variable here is really what Colin mentioned earlier, that we can actually do the export capability. So if you set py file as true, it won't generate the model in OpenSees space, but rather it will output a py file of your model with all the OpenSees py command, which on execution, when you run that py file, it will create the same model again. whether it be in a different workspace or running it separately in another machine. Yeah, but by default, if you run after you create the model, the model variable here, running create OSP model function will generate the models in OpenSees framework space. So the moment you run this, it creates the OpenSees model, which you can interact using from here. You can interact using the OpenSees command, like getting the elements, getting the nodes, or just adding loads itself. Yeah. And a good way to know that is if whether my model has been created after I run create OSP model is that we can plot the model. So what we're doing here now is we can plot using OpenSees Pi's visualization module. We have the first get rendering library. That's OpenSees Pi's first visualization module, and just running that with our OSP Grillage already pre-imports there, because we're wrapping OpenSees Pi. It will just run. You just call OG, and then the imports for it is OpenSees Pi PLT for get rendering library, plot model nodes, and it will plot the model as shown. So this kind of like a good sanity check that our model is up and running in OpenSees Pi framework as well. Doing the same using the newer OpenSees Pi visualization library, OPS and Vis, is the same thing. It's imported as OPSV. We do plot model, and this is exactly what you saw earlier in the introduction slides here as before. So there we go. We only more or less 17 steps. You are able to create your Grillage model, and that's the power of OpenSees Grillage. It wraps all the commands that you will use, which is like for this model itself would take more than like 100 lines to create, to generate the model in OpenSees Grillage. And so with OSP Grillage, more or less than 20 lines, you can create the model in the model space here. Colin, do we do a break or do we move on?
Oh, let's. I think we'll keep going. Yeah, thanks.
Yeah. Okay. Yeah. Thanks. Okay. I would say the second main feature of OpenSees Grillage is not just the first. The OpenSees Grillage doesn't just create models, but it also has. It also wraps around OpenSees Pi's load analysis commands, and so we can actually conduct and add load case and perform analysis using OSP Grillage. And so from here, I'll detail some steps on how we create some load cases. So the load cases that we will try to create, we'll try to recreate these load cases here that was used in the study of Grillage model that we have. Yeah, so just before that, again, this part here will be a bit longer, but bear in mind it's more or less showing the steps. From here on, showing the steps of how to create the load cases, and also there will be some splash of like the power of Python or the power of scripting languages here. So maybe that will be helpful for any users who wish to create similar load cases as well. You can just follow the steps that we have here. The first load case is the dead load of the super T girders itself. So in our Grillage model, the dead load comprises of the self-weight super T girders and a overlay slab. The overlay slab is a 180 millimeter thick slab. So what we do is we work. What we have here is we work out the separately the Super T girder, we'll make it as its own load case, and then the overlay slab itself will make it as its own load case here, just to show, just for this example purpose, to show such to break the steps up a little bit. So the self-weight of a Super T is really what we can do is we can define it as a line load that runs along the nodes of the position, all the nodes along the positions of the beam along the cross section. So beam one has its own, all the nodes along beam one will have a line load on top of it. So here we demonstrate how to create a line load. So the magnitude of the line load, which will be 22.4 kilonewton per meter, as you see here. What we do is we are getting the density of concrete multiplying by the cross-section area of the Super T girders. For this example, we just assume this weight is more or less similar for all beams, because even though their flange width is a little bit different, but the majority of the weight is pretty much close, and so we can safely assume this line load weight for all girders along the transverse direction. So what we do here is, having this Python environment, we can adopt things like a for loop to help create our loading. So the first thing we need to do when we define load is to create load cases. So create load case is a simple API function, create load case, and just requires a name for that function right here. We can then adopt a for loop. For this example, one would typically do the following: create a load vertex. So a load vertex is for a line load, the magnitudes of the start and end point of the line load. So we want to define the starting position as the starting length of the beam, which is at position 0, and then the last point being the length of the bridge, position L, which is 33.5 meters. A line load requires two vertex. So one vertex start, one vertex end, and you create a line load in between. And so how do we create a line load? Is using create load function here. So create load function works by passing in the types of load here. So line load is one type of load. We have later on we will showcase the other types of load. So as you can see, line load, create load, we pass in the first point, which is our first vertex, which we define at the start, and then the second vertex, which is the end point of the line load at the end of the bridge here. So using create load, we create a self-weight beam. So this is an object, a line load object for the line load, and then we add this line load to the load case that we define here, which is the load self-weight load case here, using add load function. So the reason why we're having a for loop here is because we are doing it for each longitudinal beam, the beam 1 to beam 5, and so here we can just simply go loop through the positions, the exact positions of the beam, and then creating the line load for each of those beams. Last but not least, after we done all of that, after we add all 5 line loads to DL self-weight, we can then add DL self-weight as a load case to model using add load case. So hopefully this is really like the framework of how to add loads, creating vertexes, creating the load which requires the vertex, adding the load to load case, and then adding load case to the model. And same goes same goes to the overlay slab. As like I said, we define for this example, we define it as a separate load case. So what's different with the overlay slab is this time we use a patch load instead. So a patch load is a UDL over an area. So a patch load requires 4 vertices. So as you can see here, so here we create 4 vertices, and the vertices are really the edges of the grillage model. L equals to, from X equals to XL00, and then X equals to L, the width, and then across the width as well. So L and W, and then basically the whole edge of the model, all the edge of the model here. Now, similar to the self-weight, we go create load. This time, since it's a patch load, we have the load type as patch. We then go point 1 to 4 instead of earlier. Instead of earlier line load, it's just 0.1, 0.2. So same thing. Right now, our patch load variable is now create load. Sorry, overlay slab, and then we just go create load case called DL overlay, and we add overlay slab into DL overlay using add load function here. Same thing after that, adding the load case to model. So SIDL is what we have in SIDL is the asphalt surfacing. So just the road surfacing on top of the bridge deck, and also the non-structural precast concrete edge barriers. For this, we will showcase that you can have multiple load types within a same load case. So asphalt surface, the material asphalt surfacing is as shown. We have a 65 millimeter thick asphalt surfacing multiplied by its density, and this is what we're gonna do is we're gonna use a patch load to represent the asphalt surfacing. Similar to the overlay slab, we use somewhat the same vertices, and then we can really use the same vertices as defined earlier. So you don't have to really define like this, but where we're redefining it because the magnitude of the vertices is changed. It's no longer the magnitude of the overlay, but right now it's for UDL. So same thing, create load vertex, we create 4 because it's a patch load. We create load, patch load, name as for surfacing, 0.1 to 0.4, we assign them the vertices. Yep. So for precast edge barriers, it's gonna be assigned at the edges of the model. The left and right edge of the model along the bridge. And so we want to use a line load, which is more appropriate to model our precast barriers on the edge of the edge nodes here. So we use the line load. So line load, what we're doing here is we're creating 2 line loads, one for the left edge and one for the right edge. So the left edge has its vertices named left barrier P1 and left barrier P2, right barrier respectively, right barrier P1, right barrier P2. Going through the same process, as you can see, hopefully this is hopefully you see the trend as well. Create vertex, create load, and now we're creating left and right barrier, the variables for the line load. I should mention that in this example here, for this precast edge barriers here, we are using a feature called compound load. So compound load is you can have in the compound load multiple multiple different instance objects or instances of load types. So what we have here is our compound load. We will have two line loads, which is our left barrier and right barrier that we previously defined. And so compound load is really just an additional step. It's just grouping different loads together as a single load. So you can have a compound of 2 points together, 2 points and a patch together, and so forth. So we create a compound load here called barrier. The barrier then goes, the left barrier and right barrier then goes into the barrier object using add load functions again. And then at the end, we create a load case for both. Like I said earlier, we want to add both of them within the load case. So we create a load case called SIDL, adding the load, asphalt surfacing, and barrier, the compound load within the load case itself, and finally adding load case to model. So this second part here is really just to showcase that we can add multiple different loads into a single load case as compared to previously, one load case, one load type. And we also introduce compound load, that we can join loads together in the single system, and that one compounded set of loads can be assigned to the model, can be added to the model using, or to the load cases rather. Yeah. Sorry, once. Yep. Sorry, 1 second, just. Yep. So hopefully the earlier parts we showcase how to add loads to our previously defined model. Now we'll move on to a little bit more, I would say, more practical, more realistic load model here, which is actually the live load model on the bridge stack here. So the live load model that we will add is the Australian traffic load model, a 12 axis moving load model here. It has accompanying on it a patch load, which is representing the traffic load on a single lane. So that is the design traffic load lane shaded there, along with the 12 axis groups along within the design lane here. So in ospgrillage, we can create this. We can maybe some of you can start picturing that. Okay, things that are patch load, we can use a patch load. Things that point load, we use point load, and define so forth. With our bridge model, we have three design lane, and so we need to define our traffic load model somewhat 3 times. So one for each design lane position. If I may. So first we wanna having the positions of the load model here first defined. Creating a load case here first, and similar to previously, you create load case. So now we can talk a little bit more about how we create this load model in OpenSees Grillage here. So the UDL component of M1600, we can use the patch load again. This time the patch load vertices will be the lane positions. So the lane positions is that Z1, Z2, of the model. Sorry, it's closing notification. Yeah. So we have here. So we're gonna use the patch load to define our lanes. So there will be 3 lanes. So then we use 3 patch loads here. Again, the patch load, some properties of the patch loads we use is that P1 magnitude is so in the Australian traffic load model, P1 is a UDL defined across 3.2 meters. So 6 divided by 3.2, that's the magnitude. And then so this is just where we define some variables. And so for the truck axle itself, we would then use the idea of compound loads. We'll compound multiple points together to form this this truck model here, and that's for 1 lane. So we do that for 3 lanes as well. So we can do that using compound loads. Now here's the part where we start creating. So here we can use, because we're in Python environment, we can use the power like for loops to start automate generating rather than writing serial coding. We can use for loops. So what I have here is just a snapshot of things you can do in OpenSees Grillage, etc. So this function here is simply a function to create the compound load. This has recently been released in version 0.1.1. So the function here will be a bit different name, but for this example here, we just showcase that users, you can create your own. You can really create your own compound load in Python using things like for loops. Using for loops is really powerful. You can create many vertices, and then you can add the loads into load cases, add load cases into the model itself. Not to spend too much time here, we'll move on to the actual definitions. I guess it's the last variable here we need to define, which is there will be accompanying lane factors on each different lane, lane 1, lane 2, and lane 3. Lane 1 being the outer lane, there will be a factor of 1, lane 2, 0.8, and inner lane will be 0.4. And there will be a dynamic allowance factor as well of 30%. And so later on, we'll factor our loads in the load model by 1.3. This is just a small point here. We'll make a list of elements, and this will come out as well. We'll make a list of elements and store the objects that we created. So this is again another power of Python. You can actually store the created objects into lists, like you see here, M1600 polyloads, and then later on we can reuse it. Later we will manifest and see this a bit more. So this is the part where we create the existing load model here. We use a first things first, we use a for loop for each lane. Now for each lane, there'll be its own load case. So this is beneficial, and this is more so similar to practice, where you have a load case for each lane. And then this is also so that we can apply load factors and get envelopes of maximum from this just the individual load cases here. So the vehicle and patch load UDL is created here. In the for loop, we will use the create load model. this is a new function. I should say this is a new function that's recently introduced in version 0.1.1. So it's really doing what make M16 vehicle does, as you see earlier. So it creates a compound load point of all the points, and then in compound load, compound load has its own coordinate system. So compound load is not, the coordinate system compound load is separated to that of the grillage model. And therefore, after you create your compound load vehicle, M16 vehicle N, you need to set the global coordinates of the origin for the compound load. So here what we're doing is we are just setting it using the previously defined variables. We're just setting the compound load to the position of the lanes with respect to the global coordinates of the model. So like just now, lane 1 is the outer one, relying on beam 1, lane 2 is the middle, lane 3. So we're just doing that here throughout the for loop, whilst adding that defined load into our load case here. And note that we have our load case here, as mentioned before, it's in a list. So the list we can use it to recall or reassign load cases later on here. Similar like just now. Create vertex for the patch load. We start creating vertexes. It's vertice, and then go create load, and then adding load into. Adding the load into the load case. We're this time adding the loads into the elements within the load case list within M16 load case list here. So that's really what we're doing here. Finally, after creating that each individual load case, we can now add all these load cases in all these individual load case 1, load case for lane 1, lane 2, lane 3 to the model. And in doing this, we also apply the load factor as well. So what I have here is a for loop, and do add load case. And in that load case, there's an argument for load factor, and this is where we introduce the dynamic load DLA into it. So this is something I briefly mentioned earlier. So in practice, each lane will have its own load case so that the accompanying lane factors can be adjusted to envelope for critical combinations. That's why we do the 3 load case here. So yeah. Like we can combine the load case, but this slide is a bit outdated, and we're not doing it here this time. We're separating it into 3 load cases. So the next part is the moving load case. So here we want to showcase that you can, with the load model that we have defined, we can actually do a moving load case for the load model. So what a moving load case does is it will move your compound load from point A to point B, and that point B is defined using a path. So when you set a path into so you create a load case, and then you set a path to the moving load, it will move whatever loads they define in the moving load from path within the path here, within the path. So for example, we're gonna move our M1600 from the start of our bridge out before, so it being away outside of the bridge, and we'll move it across until it passed the bridge. So just briefly, the first thing we need for a moving load is the path. So the path object is really just using create points. Well, first we need to start and end point. We do create points, start and end. There's two ways you can do it. You can use create point function, or you can use the directly interact with the point name tuple, the name tuples of Python. As mentioned before, we want the truck to start outside the bridge and then move across the bridge. And so to do so, we need to place its origin of the local coordinate, the local compound system at -25, which is so that the whole truck is outside of the bridge. And then as you move, as the truck moves, we want to move it such that the back axle, while the back axle is the origin of the local truck compound load, we want to move it across the whole bridge model. And so we define our end position as L, which is the length of the bridge, L being 33.5 meters. So moving path again, create just a simple function, create moving path. You will create a path object here. So we got the path objects, and we have previously defined all our moving load cases and compound loads for the moving load. So instead of redefining here, we can just simply go create moving load in the loop. We do a for loop, create moving load. We will then set the path to the moving load, and then we just add the loads that we define for each lane 1 into the moving load. Then moving load goes into the model using add load case. We do that 3 times. We do that. We'll loop that for each lane. That's why we have the for loop here for each lane. By default, what a moving load is basically a sequence or a number of, it will split the loads into a number of load case analysis, each representing the positions of the load moving across so we are individual static load case across while the truck moves across the bridge here. And for OSP Grillage, the default increment is 50. You can set the increment to be higher, lower, up to you, but the default increment is 50. So what it does is your M1600 here is split into 50 little static load cases, which is then later analyzed here. And to close up the load case part is really just hitting the button analyze, and that will analyze all load case here. Well, I should say that analyze function here has the option to analyze specific load case, but for this example, we just analyze all the load case that we defined previously. Yeah. So that's the part for add load case. Colin, do you think we should do a break or?
No, I think let's yeah, because time is drifting away on us, so let's keep going.
Sorry.
Yeah.
Oh, sorry.
Yeah.
I'll do. Yeah.
Thanks.
Yeah. Okay. I'll do it a bit quicker this time. Yeah. Thanks. So, first feature OSP Grillage is creating the model. Second feature is we can add load case and analyze it. Now the last feature is really the post-processing part of it. So we adopted here the Python X-array module to encompass our to extract our results here. So results are obtained using a simple get results function. Now X-array, some of you may be familiar, some not. But X-array is simply 3-dimensional arrays, arrays that you can have multiple dimensions of here. So not to scare everyone with the many different dimensions here, but in simple terms, the moment you run get results, the results is a X-array format here. So everything is inside this results object here. which you can do all the X-array commands on it. And so we have this workshop here. That's why we will show you a few things you can do with this X-array here. So this is how X-array structure will look like. You have the components. Well, I should start. You have a few data arrays within the results file, results object. In simple terms, the moment you run get results, you get the results for both displacements. So XYZ translations and rotations about XYZ. All of them get stored in results object. All forces get stored. So all your bending, torsion, shear, all those results of each element, or for displacement, each node is all stored within results here. So I having here, so all you need to do is just extracting here. And so the next step we show you a bit on how you can extract. So earlier you saw that the moment you run model.getResults, you get a result file containing all the load cases. So displacement force for all load cases, we defined earlier 6 load cases, 6 static load cases, and ball for each individual moving load position load cases. You can do a specific load case. So let's say I don't want to extract the moving load results. I just want to extract those earlier, the static load cases that I defined. So just pass in a load case argument, keyword argument, a list of the name strings of the load case that you want to extract. So what I have here is the name string of all the static load cases that we defined earlier, and then the result file now, I call it static load case results, is a more reduced load X-array here. We'll have only 6 load cases rather than the whole like 100 plus that you saw earlier. Similarly, if you want to get only the moving load, you can do so, passing again the moving load name. In this example here, I pass the moving load for lane 2, and then you will get the load cases for moving load for lane 2 within all the results within the X-array. This is something to know of about our result structure. So earlier I mentioned that the displacement will be stored as a data array inside this displacement array here, and then the forces separately will be stored inside a force data array here. Reason being that they have different dimensions, because displacement is read off nodes and forces is read off elements rather. So this is a small error here. Excuse that. We also have some other variables here within the results, so you can query things like element numbers, so nodes for the elements corresponding to the element, nodes corresponding to certain element number, element tag. You can get that as well from the results. So X-array is really powerful, and that's why we chose this as our output format for ospgrillage here. Now, you may wonder, after you got the results, how do I look at only displacements? So here's how you do it. So you go, earlier we said the static load case results, only the static 6 load cases. Just go static load case, static LC results dot displacements. It will get you the data array for displacement, which you can later do to extract information. Later on, we'll show how to extract from there. But this is how you do to extract displacement components, and this is how you do to extract forces. So forces is just dot forces. Now here we go. Now here we start with the extract. So the good thing about ospgrillage is that we don't have to worry about what like what elements are, what are the element numbers, all the element text that represents beam 1 or the exterior main beam. To do this, we just simply remember how in the set member there we set our members using a name string, a set name string of standard grillage elements. You can use the same name string and running it through get element function of ospgrillage, doing member name as this one here, the standard grillage name string that we defined earlier. You can get the tags for the elements. So like here, I'm interested to see get the tags for elements in beam 1. Just run get element, and then you get the list of the element tags. Note that this is in ascending order as well, in ascending order of x direction. 20 is the first node, x equals to 0, so forth. Same goes to node tags. I apologize for not being able to see the output, but same goes for node tags. You can just go member name, but then your option instead of going elements, you go nodes, and then you're printing out, you get the node tags for those nodes that corresponds to the beam members of the exterior beam 1, of B1. Yeah. Now here's how we can do with extracting load cases. We can define a load case name, say like a list. So what I have here is a list of the previous load case that we defined in the for loop here, the moving load of lane 1, lane 2, and lane 3. Now, if I wish to extract the maximum bending moment of beam 1, I can do it again using a for loop. So the main thing to note is this line here. So this line here is a feature of X array, which you can look up really quickly in X array documentation, or you can look up our examples in the documentation page as well. We showcase a bit of how to extract this or the data array results here. So it's really just the select function here. To put it simple, select is the function you use, passing it in the dimensions you want. So the dimensions of load case being I want to extract the load cases, all these here. I want to get all these load cases here. So that's why I have in the for loop 3 lanes. So loop 3 times. Loop through for I, load case name I1, I0, I1, I2. Component I want the bending in the Z directions. And then for the elements, I don't wish to have all elements. So I will specify for the element dimension, say only the exterior main beam 1, what we saw earlier from get elements function. And with that, in this for loop here, we are cumulatively adding the maximum bending moment, and so you can read the maximum bending moment really quickly, as shown. So 5224 is the maximum bending moment, and I apologize again for not being able to see table 3 down here, but the value is 5175, I believe. Yes, so it's reasonably close to what our previous model is, I should say. We also, in our post-processing module, we also have some plotting tools we can do. This is not to say our plotting tools supersede OpenSees Pi plotting capabilities. This plotting tool is specifically for the results, for the X-ray results. We have here in our ospgrillage some functions that you can use to plot from the X-ray results directly. So here we'll showcase a few ways you can do that. So if I want to plot the bending moment of that earlier beam 1, the exterior main beam, I do as follows. I just go plot force is my main function. I pass in I pass in the model, I pass in the results, well, and then a few other arguments is the, as you've seen quite a few times, is like which member you want. So member being exterior main BA, component being the bending, and then load case, which load case do you want? Or for this case, I'll go with M1600 lane 1, and then here you go. Once you run plot force, it gives you the plot itself, MZ and XM, because XM is in the longitude direction. So this is the bending moment you can get from having the load case, from the load case M1600 L1 here. Same goes with deflection. Let's do the same for M1600 L1. Instead of using a right here, instead of using plot force, we go plot deformation. So that's why it's plot deform. Similarly, member options, but this time options being nodes, and the load case itself, you get the plots instantaneously from the accelerated results. So this feature can be useful for once you got the results, you just quickly want to see what features, what's the maximum bending moment, what's the maximum shear force. So these two functions here are really here to help you quickly visualize that. As the second last thing is load combinations. So earlier we defined some factors here. Now those factors come in handy as well when we want to do load combinations. So results, the X-ray results, we can do load combinations by simply. So first thing I should say, I'll define the load factors first. I define the load factors for each different load cases earlier. So this is according to Australian standard AS 5100. So this is for, I should mention, this is for SLS serviceability load factors here. So 1, 1, and 1.3 just for traffic, traffic and SIDR respectively. So combinations are obtained again using the same function, get results. This time passing in, if you pass in a argument for combinations, the argument being a dictionary. So dictionaries are a Python thing where you pass in, where you have a key, the name of the load case being the key, and the load factor being its value. So you do that for all the combinations that you want to choose. Run that through, get results under combinations keyword. Then you will get a condensed, a reduced X-array of the results file of the X-array. Now this is reduced in the load case direction, because what this get results do is it actually sums up, it factors the results and it sums them up across the load cases. So what you see here is really the combination results directly. So from here you can do the same thing. You can do extract. You can extract for say for only beam 1, for only beam 2, and etc. So like I said, you can extract the results again. Use it from this condensed X-array here. So this time you can see that the results are not exactly the that of table 3. Table 3 is like 9715, but this just goes to show that the load combination you can quickly calculate from using get results function. The last feature of the post-processing module is the enveloping feature. So you can do envelopes on the results format as well. So you can get maximum and minimum from the results X-array format. So what we showcase here is oh yeah, that's just showing the move results earlier. let's move on that. Yep, where is the, sorry. Yep, so envelopes are obtained using create envelope function. So create envelope function takes a few arguments. The first being the X-ray results that you need. So we have here ds being the argument for the X-ray results that you want. What I pass in here is the moving load results here, and a few other arguments like the load effects that you want to envelope, the forces that you want, and by default envelope chooses maximum, but if you want the minimum, then you have to pass in another keyword argument called maxima equals minimum, the minimum being a minimum string word for minimum, and then you get the respective envelope. So what I do here is I'm getting the results, the envelope first. After running create envelope, I run get, and this is the reduced X-array. Same thing I can do. I can extract the results for only beam 1. So what I have here, I can do select again, beam 1, and component being that, being NZ. And it will give an array of, so this is really the bending moment within beam 1. Within beam 1's elements here. Quickly go through. So we can, same thing, we can do it for load cases. So earlier you can get the values for maximum. So what I want to show here is that you can work out where that maximum occur by passing a simple argument called query mode equals true. So what this does is it gives you, instead of the values, it will give you the position, the load case names where the maximum or minimum envelopes occur. So what I have here is the same thing, just that earlier we had query mode is true, and now it tells you where the load case is. So from here you can you can quickly identify from the name of the load case that, okay, L2 at position 214, for example, has a maximum for the middle element of the beam, of beam 1. So I guess that was that for the post-processing module. One last thing we have to showcase is that we have 2 different model templates as well, other than the traditional beam grillage model. We have this shell model. A shell model is a more modern approach for modeling grillage, of grillage analysis. So instead of everything being the same plane and modeling nodes as the beam element, we offset the beam element by a certain distance here called offset beam distance, and then there will be adjacent beam nodes which are separated, which are spaced out by beam width, and then they are connected via rigid links here. So OpenSees Grillage also offer this model, this second model type, and what you can do is you can opt to choose to model your bridge using this model type here. So, which is what we have here now. We're gonna replicate the the above bridge with our example bridge really quickly with this second model type here. So of course this is a different model type. So it's a shell. It incorporates both a shell element. It incorporates a shell element to model the slabs. So within a grid, there's a shell element, and so we need to define that. So defining that is not too hard. It's just simple. All it takes is a simple slab depth, and that's all you needed for the section. So recall earlier we create section and we create member. So create section just needs a depth, and ospgrillage automatically identifies that you want to create a shell, and then it creates a cell section for you. And then if you pass a shell section into a create member function, it will then create the shell grillage member, which you then will add to the model using the same set member function. Oh, sorry, using the set shell element function instead for this model type. So yeah. So the only difference now is that in create grillage, we chose a different model type. So this is the keyword for the shell beam model, for the shell beam element hybrid model, the model approach. And then it requires a few other arguments, which is what you saw earlier, the offset beam distance and the beam width here. Optional is the maximum mesh size here. You can choose whether what's the minimum space, what is the minimum spacing between the nodes for your mesh, for your shell sizes in the X and Z direction. For this example, same goes, because set member, we set the same property, so we don't have to redefine the cross sections that the grillage member that we defined, that we already did. So what we do is we just set member, we set the same member to shell model. So shell model is now our object for the shell element model. As I said, set shell members will do that. We'll define and create the shell models on the grillage model based on your slab shell grillage members. Yep. Lastly, same thing, create model. You can do an output or not an output version, or just create it OpenSees, which is by default. And so we can visualize it. This time we can see right now. I apologize, you can't see really clearly, but we do have in the example, I believe, in the documentation. But here it's a more elaborate model. It has more nodes. It will have the offset joints plotted here when you zoom in, if you're able to. So here's the thing that we like to say that so now that we created the model, instead of going through and create all the load cases that we have earlier, you can just simply add those defined load cases to this second model here. So how you do that? Just go shell model .add load case, and we add them all here. So what we're doing here is just add all of them that we defined earlier, including the moving load cases. So this is one of the, and then right after, we just go analyze, and that just does everything that we defined earlier. So now this is really, I should say, this is really powerful in the sense that in commercial software, you kind of need to redefine your load cases, but here you can just define it once, reuse it for many models in ospgrillage here. Yeah. So analyze the model, get results of the model, and here we have the accelerate again, as you've seen earlier. And we can do a little bit of comparison right at the end here. We can just show the results of between the beam model, the first model, and this model, the shell model. So here I'm just go get element, get the shell nodes. Of course, obviously the shell elements are different, so you want to get the beam numbers, the elements of the shell model corresponding to the exterior main beam one. Then you go look for similar to how we extract for the maximum bending for all three load cases, the static M1600 lane 1, lane 2, lane 3. So we do this for loop again, but this time we do it on the shell model. And what we have here is we extracted the results, and is pretty close, and somewhat expected that the shell model is a bit lower, because the shell model represents the rigidity of the slab better, because we are using shell elements. And so in theory, that should mean that our main beam one takes in less bending moment than carries less bending moment than that of the traditional beam element. And so here's just a showcase of that. So I guess that's And with that, that's about it for the demonstration example. So hopefully that's not too confusing. Hopefully that this will be shared later after the presentation. And yeah, I'll pass it back to Colin.
Great, thanks, Justin. Yeah, that was a great run through. What I'll do is just we won't keep people much longer, but just briefly to I'll share my screen and I'll just quickly jump to yeah. So this is the GitHub repository that we're working off. We've got the documentation here. So all of the commands that Justin went through there are available in the documentation. We've got you know, kind of detailed information on the three model types that we've implemented in here, and of course there's more model types that could be implemented, and we welcome contributions from the community on that. The API is all of the functions that are in the package, and there's quite a few obviously, but you know, for example, the plot deformation, Justin, you know, he coded it, he knows it inside out, but for the rest of us mere mortals, you know, this is what we'll look up to see exactly what arguments we should be putting into that function. So it's all in there. You know, being good engineers, you probably have some questions about the package design, or you know, what's it doing under the hood. We've tried to answer some of those questions in here at a reasonably high level as to how things are being meshed, how the coordinate systems for loads, the compound loads are in local coordinates, and then they are you know, transformed into a global coordinate system. So we've got that kind of information in here. Of course, the source code is completely available on GitHub. So you know, if you're kind of really keen to understand what something is doing, you know, just dive right into the functions. Now, you know, admittedly, it is a big package. I think we've maybe about 4,000 lines of code in there, which is okay. It's not super big, but you can understand exactly what's going on. You know, for example, here's our support types that are automatically kind of popped onto the model. Yeah, so that should bring it through, I guess, the documentation on what that's doing. Look, the other thing I think in our agenda here was what we call the call to action. This is free, open source. It's a version 0.1, right? So it's not finished. It's not polished. We have tests because, you know, we're definitely trying to be good engineers here. We have tests that are run every time a commit is made to the repository. We've got benchmark results from commercial software, from established small models. So we are making a very strong effort to make sure that the outputs are correct for the inputs, right? So we've got these example projects in here, and so every time somebody makes a pull request into the repository, you know, obviously we'll check it, but we'll run those tests. We'll make sure it doesn't break any code that already exists in there, and so we have a reasonable degree of confidence in the results that are coming out. Of course, there's no warranties given. What we would like, though, from the community is if you've got you know, a problem, and somebody did email me earlier, you know, saying, look, they had a problem installing. So if you're not familiar with GitHub, just go into this issues thing here, and you raise a new issue, and you just say, you know, problem installing, and just describe your issue in here. You know, we'll make an effort to get to it, to answer you, to say, look, yeah, this is an issue with our thing, or here's where you can find a solution to this. And we're hopeful that, you know, everybody who begins to use ospgrillage will, you know, we're trying to create a community here of users. We're putting it out there. Everybody can contribute and fork this and take and make their own. We hope people can contribute into it here, and make it a better tool for the whole community. There's been a great interest in this workshop. We've had nearly 200 registrants. I think it's the only kind of freely available on open source bridge deck grillage analysis package. So I can imagine that it will have a great utility for a certain section of people. I was asked the question, you know, why this? Well, why wouldn't I just stick with my commercial software that I've paid thousands for? Well, the paid thousands for is probably one reason, but no, really, the niche of OSP Grillage is for users that are interested in generating a lot of different results in a programmatic manner. So you'll notice that the results that Justin was running through, there was no, you know, endless Excel spreadsheet manipulation involved. That programmatic approach, the absence of algorithm of manual interventions, means that somebody could, for example, you know, examine the influence of skew on the bridge deck that we just did. We set the angle to be 0. Obviously, that's for us right now. Having done that programmatic effort, we could set that skew angle to be 10, rerun our analysis, and very quickly get those results and explore the influence of skew, for example, on something of interest to us. In a commercial piece of software, that would be far more difficult because you would now be into setting up a whole new model. So the programmatic approach to bridge deck grillage modeling will have a great productivity benefit in certain sections. So I'm, just to give one example, I'm on the code committee for AS5100, and recently I ran, I think it was 110 grillage analyses to explore what the effect of a change in the rule on something would be. Simply impossible to do that, obviously, without a programmatic interface in here. Justin, we've 1 or 2 slides. I'll stop sharing. Will you just pop those slides up just to remind me what else we're to say, and then we'll just throw it open for questions. I know we've gone on a bit longer than we intended, but the hardy who are still with us may have some questions, so we'll throw it open now. Do you have those slides there? Yeah. Thanks, Justin. You can. I've probably hit all that in your work. So contribute. Yeah, we would love you to contribute, raise issues, offer PRs. That would be fantastic to kind of make this a tool that kind of serves a lot of people. That will be excellent. Yep. Next, please. Acknowledgements. Yes. So I want to acknowledge Myra Mellams. He's a postdoc at Monash University. His contributions here are numerous. He did a lot of testing on it, and also contributed the wonderful logo, which is fantastic, and some of the images that were in the presentation today. So thank you, Mara, for that. The Institute of Structural Engineers Australia Regional Group supported this presentation, and the university, of course, supported kind of you know, allowed us to engage in our passions on this space. I think, Justin, is that with that, we'll just throw it open to some questions, comments, yeah, whatever people are interested in. I probably need to figure out some Zoom thing here and allow participants to unmute themselves. So I think you should be able to unmute yourself if you've got any questions. If you want to have a chat with us, we'll stay around for a little bit. Look, what I might do is just turn recording off, and maybe people will be more comfortable to have an open chat if that sounds good.